So we're going to start from where we left off last class, which is from vectors, right? So now we're going to look at forces. So the first thing about forces that we are going to look at is the type of forces that exist, all right? So forces are grouped into two categories, right? But before we look at forces, we need to know what exactly is a force. So anyone wants to give me the definition that you have for force?
I think it is any action that causes an object to change position, move faster, move slower, or stop.
All right.
A push, pull, or a twist.
All right, no problem. So it's any action, right? Because sometimes when we say push, pull, or squeeze, we try to sometimes forget one of those terms. So it's okay to say just any action that causes an object to change its shape, its size, its motion, right? Or its state of rest, right? So that's what a force does. So, so it's any action that changes its state of motion, it being at rest, or its size, or its shape, right? Now, we know that force unit is measured in newtons, right? And another unit for newtons is a kilogram meters per second squared. And we know that F is equal to ma, F being the force, m being the mass of the object, and a being its acceleration, right? Now, these are the specific actions that we know a force can cause objects to do. So it can cause it to stop, can change direction, right? So we look at what we know as the net force or the resultant force. So it's just similar to what we did last class, which was the resultant vector, right? So it's a single force that acts and causes a change in the state of motion of an object, right? So with balanced forces, because it's a type of resultant force, if forces are balanced, then that means they're going in opposite direction and of the same value, right? So if we're pulling, we have two persons there pulling on a string. If they both pull with the same force, they're going in opposite directions. So their net force would be 0. And in that case, no one will be moving, right? So that's what net force means, that the force is 0 on the object, so therefore there's no motion on the object, right? Same thing for the second figure, which shows the two persons pushing on the ball, right? So there's no motion after those two persons pushing with the same force. Now, unbalanced forces now would mean that one of the forces is greater than the next, right? So both forces are not equal. So therefore, you're going to cause a change in motion or a change from being at rest or change in size or shape, right? So that's what those figures show us, right? So there is another example. Top figure shows that both forces are equal, pulling in opposite direction. So therefore, there is no net force, so no one is winning, right? But when the left side now increase their force, then we notice that it's actually pulling to that side because now it's an unbalanced force acting on this system. All right, so now let's look at types of forces, right? So forces are actually grouped, all the forces that we know are actually grouped as two categories. Anyone knows those two categories that we group types of forces under?
Kinetic and potential.
Kinetic
What
and
am I talking
potential.
about?
No, that's something else. Contact and non-contact. Great. right?
I've never heard that.
So we categorize all types of forces as being either it's a contact force or it's a non-contact force, right? So a contact force, anyone wants to tell me what a contact force would be? Not an example, but a definition that we can use for contact forces. When object need to be touching for the force to exist. All right, so contact forces means basically, well, the two objects or any amount of objects that exist needs to be touching. All right, so it basically stated that what's causing the force will have to touch what will actually cause a change in the state of motion or rest. So both have to be touching for the force to exist. So therefore, non-contact would mean that they don't have to touch in order for you to experience the force. All right. So let's look at the types of forces that we have. Right. So let's look at type of contact forces first. So we have applied force. So applied force is basically the force that you exert on objects. So it's the push, pull, squeeze, or twist that we exert on our everyday life. So we're pushing an object or we're kicking a ball. So those are applied forces, right? Normal force. So a normal force is actually what physics would call a virtual force that's exerted on an object when it's in contact with a next surface. So if we look at the book on the table, right, it has a weight, the book has a weight going down on the table. So the table actually exerts an equal force going in the opposite direction, right? And that's known as your normal force. So your normal force is the exact value that is the weight of the book is, but it's going in the opposite direction. So the same thing as the person sitting on the chair. So the person's weight is acting down on the chair, and the chair will exert that upward force known as your normal force equal to the weight of the person. But the question here is, what if the person's weight is greater than the normal force that the chair can exert? What will happen? So if the person's weight is greater than the normal force that the chair can produce, what will happen in that situation? The chair will break.
Collapse.
Great.
Yeah.
Right? So the chair will actually break because it's now being an unbalanced force. So there's a net force acting down on the chair that will cause it to break. All right, and then we look at air resistance. So we know that anything that moves in air will have a resistive force, right? So if we're going up, then the air particles, the friction on the air particles will cause a downward force. If we're going down, the friction on the air particles will cause a upward force. So air resistance is a resistive force that always try to slow the object down, trying to stop it. All right. And then we have the tension force. So with tension force, it's in strings. So it's a restoring force in strings that try to actually not cause a string to break, right? So if we have, for the first figure out there, we have the tire that's connected to the string. So the tire's weight is acting down. So the string now has a tension going up, trying to ensure that the string does not extend beyond a specific length or break, right? So the tension is a restoring force or a resisting force from your applied force. So for you to have tension, you have to have an applied force that's being acted on the string. So if you just have a string that's there, then there will be no tension. You have to apply a force to it for the tension to be created. That will be in the opposite direction. And then we have spring force, which is sometimes called the elastic force. And this now is the same as tension, but it only works in springs. Right? So springs or elastic objects have a elastic force, and it's also a restoring force or an opposing force based on the applied force that's being acted on. So if we have a spring and we compress the spring, right, then the the elastic force will cause it that when you remove that applied force, it goes back to its normal position. Same as if you stretch the spring, and then you release it, the elastic force will cause it to restore
Is
back
it?
to its
Where's that?
original. All right,
Again?
and then we look at frictional force.
Very.
Right, so frictional force is once two objects or any amount of objects are rubbing together. So they're in contact with each other, but they have to be moving on the same surface, right? So just like the tires of your car on the road, the tire is in contact with the road, so you're having a frictional force. And also frictional force is a opposing force. So if the net force of the car is going forward, then your frictional force is going backwards. And the purpose of that is to try to stop the tires from moving, right? And we know that friction, once friction is present, we always have heat that is produced. All right, so let's look at non-contact forces now. All right, so the first one is a gravitational force. So this force is basically created based on Einstein. His first explanation of gravity was that between two large masses, all right, there is an attractive force between those two large masses that we experience as the gravity here on Earth. So we know that at the center of the universe, our galaxy, we have the sun, right? So between the sun and Earth, there is an attractive force between those two masses. So therefore, once we're in the atmosphere of Earth, we're going to actually experience that attractive force that always try to seek to pull us back to the center of the Earth, right? So that's the purpose of gravity. It's a downward force that causes any object or masses to actually pull to the center of Earth, right? So any mass has gravitational force between it, right? So even two persons standing, there is a very small gravitational force between those two persons. But the gravitational force is only felt great when it's two large masses. So that's why it's only felt with planets, right? So if you go continue further in CAPE, then you learn about the equation and you'll see why it's only applied to large masses of objects, right? But because humans are very small masses, then you're not able to actually feel that connection force between two persons, right? So that's what gravitational force is. And we know that on Earth, the gravitational acceleration tells us how fast objects will actually fall is 9.8 or 10 meters per second squared, right? And if we go to the moon, we know that it's less, which is 1.63 meters per second squared, right? And we know that because we have gravitational force on Earth, then we have what is known as weight, right? So the gravitational force is also known as weight, which is the effect that gravity have on any object, right? So it depends on your mass, right? Because G on Earth is the same. So if you have a weight that's different, then it has to be that their masses are different, because we know that weight is equal to mass times gravitational acceleration. We look at electrical forces. So electrical forces is a force that exists between charges. So it's either attractive force or a repulsive force, right? An example of that would be your lightning that you see due to charges in the atmosphere. Then we have magnetic forces, which is very common, right? So it exists between magnets or metallic or magnetic objects that causes attraction or repulsion of metallic objects, right? So those are the forces that we have, right? So again, we have two categories of forces, the contact and non-contact forces. Contact means that they have to be touching for the force to exist. Non-contact means that the forces don't have, the objects are not in contact with each other and they still have a force being felt, right? So there are, I think there are like one or two more forces that's not mentioned here. Anyone can actually tell me which major force was not mentioned? Frictional? No, we did actually talk about frictional. Nuclear? Yes, so nuclear is one. There is also another one. New upthrust. Yes. All right, so nuclear and upthrust forces are important. So nuclear is where the forces between your subatomic particles, your protons and your neutrons in your nucleus, right? So those forces that causes it to actually attract with each other to maintain in your nucleus. And your upthrust or your buoyancy force is the one that experience in a liquid. So it's that upward force that's experienced with objects in a fluid, right? That so this is a type of force that causes objects to float in water or any liquid, all right? So those are the types of forces that's needed for the CXC. All right, so we're going to actually now move on from types of forces. All right, so we're going to look now at moments. All right, so anyone wants to give me the definition that they have for moments? Yes, any definition there for moments? Moments, the product of the force and perpendicular distance. All right, so also known as torque. All right, so yes, we know that moments is also known as torque. So those are the same terms, right? And we know that moments formula is the force multiplied by the perpendicular distance away from your pivot point, right? So this symbol here means that it's at right angle. So your distance, your force acting away from your pivot point needs to be acting at right angle to that, right? So in moments, so actually moments, a simple definition is the turning effect of an object at a pivot point, right? So that's what a moment is. So it actually explains how easily an object can rotate about a pivot point, right? So if we have a door that has a hinge at the center, and that's your knob, right? So this is the hinge. So that's your pivot point right there, right? So we know if we push on the door, it's going to cause it to swing about this specific point here. Now, there's a key part of knowing why does your knob on your doors always it's always in terms of your length of your door, it's always in the center, very far away from your hinge. Anyone wants to try to explain why my knob is not close to your hinge or is at the top or at the bottom of the door? Yes, any response? Because of the different force applies? No, not exactly for the explanation. Let's see, because of line of action from the pivot point must be present. Someone else says because the closer to the pivot, the harder it is to apply the force. All right, so the answers are actually in those three responses. So let's put it together and get the correct or the complete answer. All right. So remember, moments tells us how easily the object can rotate about the point. And the purpose of your door is to actually get easy rotation about your hinge point, right? So for you to have rotation, you need to have a force that's applied and you need to have a distance between the pivot point and where you're applying your force. So let's examine if our force that we're applying, and let's say we're not going to apply more than 20 newtons of force, right? So if we push the knob close to the hinge right there, and let's say this is 1 centimeters away, right? And we apply that 20 newtons force, right? And if we compare it now to applying this same force, and let's say this is 15 centimeters, we can see that if we multiply the same force by the difference in their distances, we notice that the one that's further away from your hinge will cause a greater moment. And a greater moment would mean that it will easily rotate or swing around the hinge point, right? So that's one. So that's the reason why it's actually placed further away from your hinge to ensure that you have a greater distance, all right? And you don't need to use a lot of force in order for you to open or close the door, right? But let's look at now why it's actually in the center and not at the top. So if we're supposed to put the knob at the top, so you have to reach up to the top to try to push the door or open it, right? Then that means, remember, this is perpendicular distance. So you would have to actually, this is not the distance that you'll be using. So that distance will not be used, right? So you would have to actually find the right angle you would have to find a right angle distance, which is going here and then going up in order for you to actually get the distance between that force and the pivot point, right? So that's the, and if we notice, it's going to be a smaller distance compared to this one, right? So this distance will be smaller compared to this one here, and if we have a smaller distance, you're going to have a smaller rotation. So that's the reason why knobs are placed in the center of your door, right? And it's also placed extreme end of the opposite to your knob. So opposite to your hinge, sorry. So your hinge is on this side, your knob's always on this side. And even if it's a double door, if it's a double door, right, and we know the hinges are on the side, then your knob's always close to the end of each of those double doors. Right? So we want to create a great distance, D, right? Because we need to use less force, so we don't want persons to be pushing with a great force in order for the door to turn. All right? So that's the purpose of your knobs on your doors. So that's moments in its nutshell. All right? But let's look now at example of a seesaw. Right? So we have a seesaw there, and we notice or we know that if we put a person here or an object there, right, and no one is on the next side, then the the seesaw will actually fall down like that. So this part goes down, this part goes up, right? So we notice now that it will rotate about this point here, which is your pivot point. Now, with moments, we actually look at what is known as your conservation of moments, right? Which tells us that if we need to ensure that if we put an object here, we can also put an object on this side to ensure that there is no movement of your seesaw. And if there is no movement, then that means the seesaw would be in equilibrium, right? So for you to have equilibrium in terms of moments, if an object is pivoted at a point, right, then for it to be in equilibrium, there has to be a specific criteria that is met. Anyone knows that law for the conservation of moments? Let's go, let's see so what does the law of conservation of moments tells us? The clockwise moment must be equal to your anti-clockwise moment. Great, right? So for any object to be in equilibrium, then the clockwise moment has to be equal to your anti-clockwise moment. So now we need to know, how do we know which one is clockwise and which one is anti-clockwise, right? So let's say we put object B there, right? So we notice if we have two forces A and B on opposite sides, their weight is always going down, right? So their forces on the seesaw will be going down. So the easy way to find the direction that they will rotate is to actually, let's say we're looking at A. If we cover A, right, and we notice that it will cause the seesaw to actually fall down, right? So we all can do is to continue this line to your pivot point, and it gives us your rotational direction. So that means A will be rotating in this manner, right? And this here would be our anti-clockwise. So our anti-clockwise moment would be for A, right? And if we do the same for B, we connect it going to your pivot point, then we notice it's going in a clockwise moment. So therefore, clockwise moment will be caused by object B. So that's how you know which one is clockwise and which one is anti-clockwise, right? So there is also another criteria. So in this case, these two will be equal, right? So that's one criteria for the seesaw to be balanced. There's also another criteria that's outside the law that actually will entail us to know that this seesaw can be balanced when we have A and B on it. Anyone knows that criteria? So the first criteria was the law, which states that these two have to be equal. There's a second one. There must be no resultant force acting on the object. All right, so I know what you're saying, but I don't think everyone will get that. So can you break that down for me? The sum of the forces in any direction is equal to the sum of the forces in the opposite direction. All right, so we can work with that one. So that's specific, right? So the direction of your forces, right? So in one direction, those total forces have to be equal to the opposite direction, right? So for this seesaw, we only can have downward and upward forces. So for the second criteria, we know that your upward force would be equal to your downward force, right? And in this case, what would be your upward force in terms of what would cause an upward force in this situation? The pivot. Great. So your upward force will due to your pivot. So therefore your pivot will be acting, will be given an upward force there. Let's call it C. So your pivot force would be your upward force, and your downward force will obviously be your A and your B forces. Right? So A plus B force will be equal to your pivot force, and your pivot force is a type of force that we just did. What type of force will be experienced by your pivot? So what type of force will be at your pivot? Will it be friction, upthrust, any one of those? Which force is experienced because of the pivot? Friction? Any other answers? Applied force? Any other one? All right, so those are the normal force, all right? So those are your options, all right? So let's look at each option and see if it's viable. All right, so friction. So if we look on your seesaw, all right, we're not seeing where there's a rubbing process going on between your pivot and your seesaw there. So in that case, we will not be able to confirm that C would be friction because there's no rubbing there, all right? And applied force. So applied force, so the applied force would be A and B, right? Because those are the two things that cause enough force on your seesaw. So it's So the force that's at C is actually not an applied force because there is no object that's placed at C to cause you to get that upward force. So therefore, or answer would be a normal force. And it's a normal force because the seesaw is placed on your pivot point. So therefore, your pivot point will send back an upward force. Sorry there. So your pivot point will send back an upward force. That is a virtual force going up, right? Because your seesaw is going, weight is going down on your pivot, right? So that's that force there. So your pivot force is also your normal force. And you sometimes will see that in your questions. They will ask you what's the normal force at your pivot, which is actually your upward force there. And you'd use this principle or this one to get that answer. All right. All right. So let's go. All right. So we just learned of moments, right? So now let's put it into practice and let's answer this question here.
What is teaching man? Sorry.
All right. So
The guy is
all right, so in this case, the question, we're going for part B. So figure 2 represents a tray held vertically, horizontally, sorry, by a waiter. The tray has a weight of 6 newtons and supports a drink of weight 3 newtons. The waiter provides a force at P. The tray must pivot at point T. So use the information in figure 2 to find the force provided by the waiter at point P and the upward force of the hand exerted at T. All right. So the first thing is to actually just resketch the diagram to actually eliminate all the unnecessary figures that's present. And to do that, all we need is just a horizontal line for the tray, right? And then at this point here, we're going to put a downward force for your drink, and it's 3 newtons, right? And then in close to the center here, we have a downward force as well, that is 6 newtons, right? And then we have point T, which is your pivot. So T, we're going to note as your pivot point. And then finally, we have a point P here, which is unknown. Right? So those are the forces that are present, and the distance would be that the 3-1 away from your pivot here is 40 centimeters. The 6, so this distance here is 5, and this distance is 30. Right? So the first part of the question is to calculate P. Right? So the first thing is we need to calculate P. Right? So we notice that we don't have the force at your pivot point, so we can't use the second criteria. So we have to use the first to state that our clockwise moment is equal to your anti-clockwise moment. So the sum of your clockwise moment will be equal to your sum. So anti-clockwise equal to clockwise moment. So now it's to determine which forces are clockwise, which one are anti-clockwise. So let's go. Which forces will be going clockwise? Which ones will be going clockwise? All right, someone says the 6 and the 3 will be going clockwise. Next person, 6 and 3 clockwise, P is anti-clockwise. All right, so let's go. So we remember we just continue our direction of our forces to your pivot point. So that's going like that. This one is going like that. Right? So these two directions, 6 and 3 will be anti-clockwise. So it will go here. And then P is going like that, which is clockwise. All right, so great job, guys. So the anti-clockwise tells us, remember moments would be your force, right? And we're going to call it 6. So your force of your 6 newtons times your distance plus your force of your 3 newtons times your distance. So those are the two anti-clockwise. Is equal to your clockwise, which is P, the force at P, times your distance from your pivot point. All right? So you guys are going to help me help, right? So we have force of 6, which is 6 times the distance away. So what's the distance away that 6 is from your pivot point? Twenty-five centimeters. Where are you confused at? All right, so since one person is confused, I'll redo everything from here. All right, so remember to find the direction that they're going to rotate. We just continue our arrows towards your pivot point. So 6 will continue like that, 3 continues like that. Right? So these directions will be anti-clockwise. So 6 and 3 will be going anti-clockwise, while P continue like this will go in our. Sorry. So these are clockwise. So 6 and 3 is clockwise, and P is anti-clockwise. So 6 and 3 clockwise, and P will be anti-clockwise. Right? So now we substitute. So the force at 6, which is 6 times the distance away, which is this distance. So we have this distance, which is 30, and this is 5. So 5 minus 30 gives us 25. Right? So we don't know what. So remember, it's 25 centimeters. So we'd have to convert it to its base unit, which is meters. So we divide by 100, so we get 0.25. Right? All right, and then, so that's your 6, and then for the 3, multiply by the distance away, which is, what's the distance away for the 3? Forty centimeters, which is 0.4 meters. 0.4 meters, right? And then the force at P, which is unknown, so force P times the distance away from the pivot, which is, or 5, so we change that to meters, which is 0.05. All right, so now we can do our math. So 6 times 0.25 is 1.5 plus 3 times 0.4, which is 1.2. right? And then we have 0.05 FP here. We add these two, we get 2.7, right? And then we divide by 0.05. So FP would be, which is 54 newtons. Right, so that would be the answer for your force that the thumb will exert on the tray. All right, so everyone got that? All right, great. All right, so the second part of that question says, what's the upward force at point T? So remember, this is just like your seesaw, right? So the upward force at T would be your normal force. So in that case, we notice now that we have all the downward forces. So we can use our second criteria, right? That says, so for part B, then the T force will be equal to the force of your 6 plus the force of your 3 plus your P force, right? So T would be your 6 plus 3 plus 54, which is 63 newtons, right? So we have our 3 downward forces, and that will be equal to your only upward force, which is at point T. All right, so let's look at the second part for this question. It says, the drink is moved along the tray close to the hand. Is the force needed at P to keep the tray horizontal less, no less, greater, or the same? Explain your answer. All right, so I'm throwing that one to you. Could the second or this one? All right, so for this one, it asks us to find the force exerted at the point T, which is the fingers. So you're holding a tray like this. So these fingers are creating an upward force, right? So we notice that because the tray is in equilibrium, so it's perfectly horizontal, then that means your downward forces will be equal to your upward force. And the only upward force is at point T. So if we add our downward forces, it will be equal to that force that is present at the point T. So what we did was to add the 6, the 3, and your P force, which is 54, right? So we get T force to be 63 newtons. All right, that's okay now? Okay. All right, so now let's hear the reason now. So if it says, let's repeat, so if the drink, so if we have the drink with the 3 newtons, say if it's actually moved closer to point T, right? So nothing here changes. So T and 6 is the same position, but we move 3 closer. So we move it, let's say we move it to this point here. What effect will it have on the P force? Will it cause the P force to remain the same 54, or will it increase from 54 or decrease? All right, so we have an answer here. It says it would be less because the distance of the force from the pivot would be less, and hence the amount of force required would be less. All right, so yes, that's correct. Right? So what we're looking at is the only thing that we're changing from this situation is that we're changing this value from 0.4 to to a lesser number, right? So if we use a lesser number than 0.4, then this number is going to be less, right? And if this number is less, then this is less. And if we divide this by a lesser number, we're going to get this to be less as well, right? So in that case, your P force would be a lesser number because we reduce the distance of this force. So in that case, we're reducing your turning effect. So this now has a lesser turning effect. So therefore, we need a smaller force to counter that lesser turning effect. So that's the reason why. All right, you got that? All right, great. All right, so we're going to do one more. All right, so we're going to look at this one. All right, so it says the forearm is a lever in which the bicep muscles provide an upward force which can raise the arm and carry a load. The diagram below represents the forearm as it holds a load of 60 newtons. The forearm has a weight of 25 newtons and the center of gravity G of the forearm is marked along with the point P at which it pivots on the adjoining bolt. All right, so use the principle of moments to calculate the force B exerted by the biceps to hold the arm and load stationary. All right, so we know that it is in equilibrium. All right, so remember the first thing is to remove all unnecessary things from our diagram. So again, we're going to start off with just a straight line, horizontal line, and add in our things. All right, so we have our load here, which is 60 newtons, right? And then we have point G, which is a downward force of 25 newtons, right? And then we have B, which is an upward force, and point F,
Yes, sir.
right, which is our pivot point. So F there is our pivot, right? And then our distances would be between these two is 0.15 meters. This is 0.20 meters. And this distance is 0.05. All right, so that would be your diagram when we eliminate all of the other figures from it. All right, so the purpose here is to find what is your B force. So we're calculating B. All right, so again, we are going to use the principle that states that our clockwise would be equal to or anti-clockwise. So now it's your time to tell me which one is clockwise, which one is anti-clockwise.
G and the load is
It
clockwise.
happens.
G and the load is clockwise.
G and loaded
Load.
is clockwise.
Clockwise.
Okay.
Uh,
And B will be anti-clockwise. That's what everybody has. Great. All right. So Just for purpose, let me connect and show. So 25, continue like this.
Can you repeat, please?
Sure. So the 25 force going down, so we continue it to our pivot point. So that shows it's a clockwise motion, right? Or 60 going down, so we connect it up to our pivot point, also going clockwise. And then these going up, right? And if it's going up, let's see. So it's going up, and we continue to our pivot point, then that is a anti-clockwise. So we have 25 and 60 going clockwise and B going anti-clockwise. So let's write that. So F of 25 times D plus F of 60 times D equals the anti-clockwise, which is B. So F of B times D, right? So let's put in our values. So F25 is 25 for force, and the distance away from your pivot point of 25 to F is 0.2, right? Plus F of 60, so the force is 60. All right, I'm sorry about that. I have no idea what just happened. All right, so continuing, what would be the distance of the 60? Yes, what's the distance of your 60 Newton force?
Zero point 0.35.
0.35. Right, and that's equal to force at B, which is unknown, times the distance away from B, which is 0.05. All right, so let's calculate these. So this is 5. 21 equals 0.05 FB. All right, so this is 26. So we get 520 newtons. All right, so everyone good with that?
Yeah.
All right. All right, so that's the all right, so the second part says the adjoining bone pushes down on the forearm at the point P. What is with a force R? By considering the upward and downward forces, calculate the value of R. All right, so for the second part now, it's saying that we're introducing a downward force, calling it R, that's at F, right? And we need to know what that force is. So in this case, again, we're going to use the second principle, which states that our upward forces would be equal to or downward forces. So we need to identify our downward forces, which would be the 60, the 25, and the R. So we have downward equals upward. So for downward, we have 25, we have 60, and we have R. And then upward would only be B, and B was 540, 520. And B was 520. Right? So here we have 85 plus R equals 520. So R is equal to 520 minus 85, which is 435. All right, so that's clear for everyone. All right, great. All right, so with moments, this is the same process you do for each single question that exists for moments, right? So the simple part is to revise your diagram to make it clearer, right? You identify your clockwise or anti-clockwise forces, and then you calculate your values, all right? Now, so that's it for moments, right? There is nothing else that is present, right? So we're going to actually, the question? All right, so we're going to actually move on now to something a little more easier. We're going to look at Newton's laws, right, of motion. So we're looking at Newton's law of motion. So we know we have the three laws, right? So meanwhile I'm talking, you can actually start writing law 1, 2, and 3 for me, so I can see. So we know that Newton actually described objects moving based on his three laws of motion. So every object that exhibits motion will actually fall under one of these laws. So we have the three laws of motion that explains objects that move. All right, so the first law, which is also known as your law of inertia, which states that
I don't even remember. Every object will remain at rest.
An object will continue to move in a straight line unless acted upon by a net force.
right, so object continue to move on a straight line unless acted on a net force. That next person has a body at rest or in uniform motion in a straight line will continue unless acted upon by a resultant force. All right, so we can go with that one there. Right, so if an object is at rest, right, so if you're sitting, not moving, the only way you can actually change that state of not moving is to actually exert a force. So the net force on you right there is 0, right? Because nothing is moving. So there has to be an unbalanced force that will cause you to either get up or to fall down, right? So that's the rest part. And also objects that are moving in, if there is no external force, meaning that there is no air resistance, there is no friction, right? Then that object will continue to move in a straight line. So if we have a vacuum and we have a ball rolling on the ground in that vacuum, it will always just move in a straight line and it will never stop, right? But we know in everyday life that's not possible because we have friction, we have air resistance that will cause objects to slow down, we have breeze that will cause it to change direction, right? But Newton states that if we eliminate all those external forces and an object is moving, it will move in a straight line, right? And the only way it will stop moving in a straight line is if there is an external force, which is an unbalanced force, that will cause it to change direction, right? So it changes direction, move left or right, right? So that's what his first law states. And his first law, again, is actually known as your law of inertia. And what's inertia?
States that every object will remain at rest or in uniform motion in a straight line. Something like that.
That's the law. What's the definition for inertia?
Oh,
Tendency of a body to stay at rest or in motion.
Great. So inertia is the tendency of objects to stay at rest, right? So easy an object is when you apply a force that will remain at rest. So that's what inertia is. So if you have high inertia, then that means it requires a very high force for you to actually move, right? So that's what inertia is, right? So that's our first law. And our second law, right? So what's our second law now? Second law states the rate of change of momentum of a body is proportional to the applied force and takes place in the direction of the force. A lot of big words. What is correct? All right, next, the rate of change of momentum is proportional to the applied force and takes place in the direction of the force. All right, so now those laws actually applies to a new term, momentum, right? Which we're going to look at next. So the law, the second law, actually talks about the change of state of momentum. Let's break that down into objects speeding up or slowing down. So that's what rate of change of momentum is. So if you're changing momentum, that means you're either speeding up or you're slowing down, right? So objects will continue to move in the same speed, right? So just imagine a car moving at 50. So it will always move at 50 unless you apply more force, which causes it to speed up, or you release your foot from the gas that causes it to slow down, right? So that's what the second law states. So you're moving at a constant speed. You will always move at that constant speed unless you apply an unbalanced force, which would cause it to speed up or slow down. All right, so that's the second law. And then final law, if body A exerts a force on body B, then body B exerts an equal but opposite directed force on body A, which is simplified by saying every action has an equal but opposite directed reaction. Right? And that one is simple. So normally if you thump a wall or you fist a wall, the wall basically gives you back that same force back on your hand. So that's the reason why if you hit it hard enough, it actually causes damage to your hand because that force is sent back to you, right? So that's what the second law states, that if you apply a force to any object, that object will apply that same force in the opposite direction back to you, right? So those are his three laws that actually explains every form of objects that move, right? So basically to know those equations, right? Well, not equations, but the laws, right? And just word for word, right? So this is the only thing that we actually try to memorize in physics, the laws, right? So you remember the laws and know how to explain it, right? So let's go again. So the first law, the law of inertia, right? Which in explanation states that if you're at rest, the only way you cannot be at rest is if you have an unbalanced force that causes you to change from being at rest. Or if you're moving, you're moving in a straight line unless you have an external force that causes you to change your direction from being in a straight line. Our second law states that if you're an object moving with a speed, will continue to have that same speed unless an external force will cause it to speed up or to slow down. All right, and you can use like the car example to finish explaining that. And then the final one would be that whatever force is applied to an object, the object will exert that same force back onto the original object in the different direction. All right. So those are the three laws of motion, right, that Newton uses to explain objects that are moving. All right. All right. So let's look at momentum. All right. So what exactly is momentum?
Momentum is the quantity of motion that an object has, something like that.
Not exactly. All right, let's see what someone else says. Momentum of a body is the product of its mass and its velocity.
Yeah.
Right? So, as again, remember the first class, we can use our equations to define our quantities. So exactly, so we know that momentum is mass times velocity. So it's the product of your mass and your velocity. Or it's basically telling us it's the effect of objects that are moving. So any object that is moving will actually have what is known as momentum. So if you are not moving, then you don't have any momentum because you don't have a velocity, right? So we know that P, which is the symbol of momentum, is equal to your mass times velocity, right? So P, momentum, is equal to mass times your velocity, right? All right, someone is working with me here. So the unit of momentum is kilograms meters per second, right? So we know these things from our momentum here, right? So the unit kilogram per meters per second, kilogram meters per second, sorry. Now with momentum, since only objects that are moving will have momentum, then once the object is at rest, its velocity is zero, so therefore it has no momentum, right? Now let's look at the conservation of momentum, because once objects are moving, right, it will have the tendency to actually collide with other objects. So once you're moving, there is a tendency to collide, which will cause you to change your momentum. So it's going to either get it to go higher or lower, right? So, but in that entire system, we know that that momentum is conserved, which we know is the law of conservation of momentum, right? So we know that the momentum in every collision will be the same before as well as it is after, right? And then we have Noel here that's identify our two types of collisions. So when objects collide, it either can be in an elastic manner or it's in an inelastic manner, right? So let's look at each, right? So what does the elastic one tell us? So once you have a collision that's elastic, what does that mean?
Elastic, elastic collision means that when two particles collide,
What is it?
the amount of momentum. When two particles collide, the momentum transfers from one particle to another, and they move in the same direction at the same time.
I didn't get the last part of what you said. You want to repeat that, the last part, please?
So talk to you.
Yes, anyone wants to tell me what elastic collision entails?
Elastic collision is like the collision in which there is no loss of kinetic energy in the system.
All right, so there is no loss of kinetic energy. All right, so how do we know when a system is at elastic collision?
When they're going in the same direction.
No.
After collision, they do not stick.
Great.
They bounce off.
All right, so we know that it's elastic when they bounce off. All right, so it's just like hitting a wall with a ball. All right, so each time the ball hits the wall, it actually bounces off. Right? So that's our elastic collision. So we know in that case, kinetic energy is conserved and the objects, they bounce off each other. Right? So in that case, inelastic would mean that the kinetic energy is not conserved. So it's not conserved. And in this case, they will stick together. Right? So when the objects hit, they will go ahead and stick together. Right? So it's important to know how you can differentiate the elastic and the inelastic collisions. Now, we should note as well that momentum is a vector quantity. And by vector quantity, all right, let me look at what Noel is saying. In real life, elastic collision doesn't really exist due to the transfer of energy from state to another. All right, so that's very important to highlight that this conservation of kinetic energy is not actually realistic in everyday life, right? Because when objects collide, right, you're going to have a little bit of noise, so some of the energy is released as sound energy, right? You're going to have heat being produced. So all those things will actually cause the kinetic energy to change its form, right? So in reality, we'll not have kinetic energy being conserved. This will only work under a vacuum situation where there is no other factors or particles present, right? So as I was saying, that momentum is a vector quantity. So it has to be known based on the direction in which the object is going, right? So because it's mass times velocity, we know that velocity is your vector quantity. So it depends on the direction in which the object is moving, right? So we note, remember when we did velocity last class, that if the velocity is going up, then we know that has a positive velocity. If it's going to the right, it's a positive velocity. If it's going down, it's a negative velocity. And if it's going to the left, it's also a negative velocity. So these signs are important when we're calculating the momentum of objects based on their
Could you
direction.
repeat that part, please? Over.
So the direction of the object is based on the direction in which your object is moving. So if it's moving upwards, you have a positive velocity. Just like the signs on your graph when you're doing a t-graph in math. So you're going up. So these numbers up is positive. Going to the right is a positive velocity. Going to your left is a negative. and going down is also a negative, right? So those tell us how we know what sign to use with our velocities based on the direction in which the object is going, right? So another thing, another term to differentiate is actually linear velocity, linear momentum, right? So CXC wants to know if you can actually define this term here, which is the same as momentum, but it has one additional part. Anyone can tell me what that additional part is? What does this linear part mean? So remember, momentum is the effect of object in motion, or it's the product of mass and velocity. But what does the linear part tells us?
It's hard up.
I'm coming to you, Nick, now. Yes, what does the linear part tells us?
In a straight line.
In a straight line? No, not quite for physics. So linear in general means straight line, yes, but for physics, linear actually tells us the plane that it's acting in, right? And by plane that it's acting in means
One dimensional.
it's a one-dimensional, right? So we know that we have different types of planes. So when you do a graph, you have your y plane, your x plane, and there's also a plane that is not there, which is your z plane, right? So if you notice when you did calculations of momentum, if an object is going to the right, then after collision, it either can go right or left, right? So we always stay in one plane. So if it's going left or right, it's always left or right. Going up or down, it's always up or down.
Oh,
So that tells us it's a linear momentum. So it's always in the same plane,
no.
right? So linear momentum is just momentum in the same plane, right? So all the objects are moving in the same
And
plane,
may I chatter?
right? So if they're moving in the x plane, they're all moving in the x. If they're moving in the y, they're all moving in the y plane, right?
So I have a question.
So that's what linear momentum is, right?
So I have
So
a
let's
question.
look at Neil. So let me go back up and see what he said. So would the positive or negative of velocity be relative? All right, so the positive or negative of your velocity is just dependent on the question direction that object is going. So if it says the object is going to the north, right, then north is up, so that's a positive. Right? If it's saying it's going to the left, then left is negative, right? So it depends on the direction that your question will give you. So that tells us what direction sign you'd put with your velocity.
Sir,
Yes?
not asking in a realistic point of view, like if I was saying that my velocity is left or right,
Mm-hmm.
to someone else it might be north or south. So
Oh,
it's relative.
yeah,
As I mean,
it's relative to the viewer and the objects that's moving. But we don't actually look at that. That's a whole topic that you will not learn until university, right? But in reality, it's based on the direction based on your observer. That's the direction that you use. So if you're looking at it, what direction you're seeing it moving in, right?
sir, I have a question then.
Yes.
So does that mean that velocity has an infinite amount of negativities or positivities that it could be in? There's an infinite amount of variations.
Well, it in a sense, yes, but based on linear momentum, it's all right. So in reality, we don't have this a lot, linear momentum, right? But when you reach like Cape physics, you're going to do the realistic part of momentum, right? Which is tells you it doesn't matter which plane you're in, it gives you a complete answer, right? Because we're going to actually look at each plane separately. But for CXC purposes, they just want you to focus on one plane to make it easier for you to understand at this point, right? And in that case, then we just look at it from the point that if it's going left, it's this sign. If it's going right, it's this sign up, this sign down, this sign, right? But in reality, when you go further, you're going to learn that an object can actually move between two planes or three planes, and how we treat it to know which sign it's going to be will be different from how we do this. But at this point, you just need to focus just on this area here to help you with linear momentum. But further on, you'll learn about other methods in those cases. All right?
Yes, sir.
All right. All right. Someone made mention of impulse. All right. So in reality, you're not actually required to learn about impulse at CSEC level, right? So it was actually removed from the latest syllabus. So you're not required to learn what impulse is. That is for CAPE students, right? But persons that know about impulse is basically it's the change of momentum. So the change in momentum is actually known as impulse, right? So you're not required to learn that at this point. All right, so
Yes, sir.
yes,
The linear momentum is just about a one-dimensional field.
yes,
So if an object, for example, like a ball, hits a wall and has the exact amount of kinetic energy and bounces off, that's elastic.
yes.
And what if the ball that hits the wall, it bounces off, but has less kinetic energy than before? It wouldn't be inelastic, but it wouldn't be elastic either. So what would it be considered?
It is actually elastic, but remember, we made mention that in real life, the kinetic energy being conserved will not actually apply. Because when you hit the wall with the ball, you're going to hear sound, so some of the energy is converted to sound, and the ball will actually rub on the wall before it actually is released. So that means you have friction, right? So in this is only for theoretical purposes that kinetic energy is conserved. But in real life situations, it will never be conserved because you're always going to produce heat, or you're going to produce sound, or in some cases light. So all those byproducts will actually change the kinetic energy from being actually conserved. But the main part to know which one it is, if it's elastic or inelastic, is the bouncing off or the sticking together. So that's the main criteria to know if it's a elastic collision or inelastic. So if it does bounce off, even if the kinetic energy is not conserved, it is still elastic collision. All right?
Sure.
Mm-hmm. All right, so let's look at elastic collision case. All right, we're going to use a pool table. So we have the white ball, and let's say we're going to allow it to move to the right. It's going to collide with the black ball, right? And then after collision, we're going to get the white ball moving to the left and the black ball moving to the right. All right, we're going to call this V1, this is V2, and this is V3. All right, so remember the conservation of momentum says that the total momentum before collision will be equal to the total momentum after collision, right? So let's look at how we write up equation to help us to calculate any unknown from this situation, all right?
M1,
So
M1 V.
let's look at the first object here. So let's put before here, and then this is after. So we have the momentum of the white ball before, which is,
M1
let's call it MW since it's white. So MW.
VW
Alright, so this is V1. So V1
plus
plus
M can't see.
MB, so that
M
ball,
plus V2
more times. Alright, so black ball here, we notice there's no arrow on it, so it's stationary. So in that case, the velocity here is 0,
0.
right? And then that's equal to, what will they have after now for the white ball?
You would have can't see. M1 V1
So we have the MW of the white ball. It's now going to the left. So this V2 will be multiplied by negative V2, right? Plus the black ball starts to move now. So it's going to be MB. It's going to the right. So it's a positive. So that's V3. All right. So we notice here that because the white ball is going to your left, we're going to actually include that in your equation. So it's a negative V2, right? The black ball is going to the right, it's a positive V3. The black ball before collision is not moving, so this momentum here will be 0, right? And then the white ball will be going to the right, so it's a positive velocity. All right, so we have everyone understand that part?
Yeah.
Yes, sir.
Right, great.
Yes,
All right.
sir.
So for any elastic collision, this is how it actually will look, right? So before collision, you have your separate velocities, your separate momentums, and then after collision, you have your separate momentum, right? This shows us, this plus sign here, shows us that the object bounced off, right? So we have separate momentum, separate momentum. So this shows us that there's a bouncing off of the objects, all right? So that's for elastic. So let's look at an inelastic case. All right, so we're going to have a white ball moving that way with V1, a black ball moving there with V2, and then after collision, they both move off in that direction with a velocity V. All right, so let's look at this one now. So let's go. What would be the equation? So before, for the white ball,
MW
MW
times V1
times V1, so that's your momentum of the white ball, plus
MB
MB
times V2
times V2. There's something missing from that?
Negative.
The negative,
negative V.
right? The negative V2 equals what we have for after now. Yes? What we have when it's after, when they stick together and move off?
Bracket.
Anyone?
sir, it's stationary, so it would be 0.
No, there's an arrow there moving at velocity v.
Oh, sir, there's a light
Really?
on the board.
Oh,
Yeah, I can't see. It's a glare.
oh, so it's there, stick together and they move to the right with a velocity v.
Still don't get it.
Yeah, stuck.
All right, you seeing it here? So after collision, this is what happens.
So B is positive.
Yeah.
Right, so we know both of them moving with the same velocity, so we can actually simplify it. So mw plus mv multiplied by v, right?
Uh-huh.
Because they're both moving with the same velocity, so we just add the masses together and multiply it by the velocity there. And
So
this,
I can't be V2, just V.
yeah, it depends on what you want to put it for. So if
So
you want to put
MW.
it as V3, VA, V, whatever it is, right? So this V here, because both objects move with the same velocity, it's called the common velocity. Right? So in elastic collisions, after collision, the two objects will always move with a common velocity because they're sticking together, so they move off with the same velocity for both objects, right? So in inelastic collisions, this is always the same process for the equations, right? So before collision and then after collision is the sum of the masses times that common velocity v. Right? So everyone got that for
Yeah.
both equations, elastic and inelastic?
Yep.
Yeah, yes, sir.
All right, great. All right, so we have little time, so we're going to pause momentum. We'll continue with some calculations next class. So we're going to look at some questions.
My calculator.
Please, sir.
Yes,
What's the massive V for though? What's the V? The V is representing one direction, right?
the V, yes, it's going to the right, yes.
Oh, I didn't see the arrow there because the light
Okay.
wasn't lit. That's why.
Sir, there's a multiplication sign between the MW and the MB.
Between which one? Please?
The MB and the MW.
But
There's
this
a.
is
No, it's a plus sign, plus.
All right.
Remember, they're moving at the same velocity, so we add the masses.
2007.
All right, so let's see how much questions we can do before this time runs out. All right, so I think we did some questions before, so we can just redo them again to make it a good practice. All right, so question 1, which of the following is a SI base unit?
Ampere.
Ampere.
A.
Yeah, A. All right, next. To measure the external diameter of a measuring cylinder most accurately, one should use a
Pair of vernier capillars.
Yep, so use a vernier caliper.
Yeah,
All right. Next 3, when used in front of the unit, the prefix mega means
+6.
A.
all right, so mega is 10 to the 6.
Mm-hmm.
Great. All right, 4, which of the following is true about the period of a simple pendulum?
I think is
A.
What's that?
A.
A.
Yes, it is A. All right,
Okay.
so remember we did that last
Yeah,
class, so
A.
we increase the length, so the time also increases. All right, and then question 5, when x is 0, the value of y would be?
U.
B. Great. All right, so that's S. D is the answer. All right, which of the following is a fundamental quantity?
Density.
Then
Mass.
boy.
Boy,
B.
B. Yes, so mass is a fundamental. All right, which of the following is not a derived quantity?
Oh, current commodities. I don't know about that.
Charge.
Could you repeat that?
Charge.
Charge?
Charge. Yeah. I was looking at
No,
that.
no, it's not charge. If it's not a derived quantity, then what type of quantity is
Is current?
Fundamental.
It's a fundamental. So remember we have 5 fundamental quantities, right? Length, time, mass, temperature, and current.
Oh, no.
So therefore the answer here would be current.
I'm
Yeah.
right.
Yes, sir. Don't we have? Sir, I thought it was 7.
Yes, we have 7, but CXC, CSEC is just for 5. CAPE is 7.
Oh. Yes, sir. Charge is a derived quantity then.
Yes, it is.
All right.
All right, so 8. A coconut falls. All right, so we haven't done our graphs as yet, so we're going to leave that one until next time. All right, an example of a vector quantity is question 10.
I'll go with.
What's the answer? Which one is
Is it
I'll
B?
do that.
Which one?
Yeah, I agree on the well. D.
Isn't it
D?
D?
Yes, D as in dog. So
Yes, D.
displacement.
Yeah, because
All right, question 12. Which of the following is the unit of momentum, which we just did? So the answer is
Boy.
boy. All right, so kilogram meters per second. All right, 14. A single force which can replace that and have the same effect as 2 or more forces acting together is known as?
Equivalent. D.
No, not B.
Oh, moment.
Moment? No.
Resultant.
Resultant.
Oh, resultant.
All right, remember we said that the resultant force is the action of 2 or more forces. All right, so it's the resultant.
Oh.
All right, so all right, let's see what you do with this one. 18. No, before 17. The rate of which of the following is not true about the moment of a force? So which one of those is not true?
Newton meters.
All right, so let's look through each. So A says it's measured in units of Newton meters. Remember, moment is force times distance. Force is measured in newtons. Distance is measured in meters. So that's a correct statement. All right, let's look at B. It is the amount of force needed to keep an object turning. All right, so that sounds not true, but let's look at the others and see. It is a turning effect that a force has when it's acts on an object. We know that's true. Right, and D, it's the product of a force and the perpendicular distance of its line of action from a point. And we know that it's true. So therefore, B is our answer. So that's boy. So it's not the amount of force needed to keep an object turning. It's the turning effect. Right? All right, let's look at 18. X, Y, and Z are 3 balls of equal masses whose center lies in the straight line. Y and Z are touching one another. X traveling with a velocity v, hits Y. Assuming that the spheres are perfectly elastic, the resultant motion after impact will be that. So what will happen when X hits Y?
I think Z would move. Can go walk up to the ball. I think Z would move.
All right, so Z will move.
Yeah.
What happens to X and Y?
Let's see.
X and Y will stick because Y will stick
All
and
right.
Z will move.
So X and Y will stick with stationary, and then Z will move.
You move.
All
So
right, so
it's
that
boy.
means boy.
Yeah.
Right? So this diagram is it's just actually the Newton's cradle. I think everyone is aware what that is, right?
No.
Repeat that, sir.
So the Newton's cradle, if you take away one and then release it, then the opposite one on the next side will move. Right? So that's what that is saying.
So wouldn't that be elastic and inelastic collision being in effect?
No, it's not inelastic only because the two first balls stop moving. Right? So because Y and X would stop moving after collision, only one thing would be moving. So you treat X and Y as one object and Z as an X. So it's not inelastic. If X and Y after collision moved off a little, then it would be both elastic and inelastic. So because they're stationary, they will not be inelastic. All right, so I think that covers
No, sir. My question was that. Sir, my question was that in a sense, like when X hits into Y, X is moving, and then as soon as it hits Y, it becomes stationary. Wouldn't that be inelastic collision? And then Z would take on elastic collision in a sense. You see what I'm saying? Like in a sense.
Yeah, you could look at it like that as well, since X and Y would actually stick after. Yeah, so you could look at it like that. All right. All right. So those are the topics that we've covered so far. All right. So
Beautiful.
And we're almost out of time. All right. So guys, thanks very much for participating today, and hope I see you guys next time. Hope you learned something new today. All right. So
Thank
bye-bye.
you, sir, for this
You're
time.
welcome.
Thank you, sir.
You're welcome.
We appreciate it.
No problem.